Okay, so this is our class 9 of week 9 assignment. Let us begin the 10 questions. So question number 1 is why ln theta phi will be a simultaneous eigenstates of which of these sets of operators. So first of all, you can see that there are L squared, this angular momentum operators are given in the options, and how to know that whether they will have simultaneous eigenstates or not is only valid if the operators you are talking about, uh, those operators, if they commute with each other, then we can safely say that they will have simultaneous eigenstates, right? So first of all, that has to be satisfied, and out of these angular momentum operator sets, which actually satisfies this, will this commutation relation will be having the simultaneous eigenstate, right? So let us go and write down our answer. So first of all, if y ln theta phi is an eigenfunction of uh, the angular momentum operators, then you can safely say that L squared y, sorry, L squared this is the eigenvalue and this is the eigenfunction of the operator L square. Similarly, you are familiar with this relation that LZ operator, so L square is an operator here. LZ cap operator, when acting on YLM theta phi, you get M H cut YLM theta phi. This is the eigenvalue, this is the eigenfunction, and this is the operator. So naturally you can see that both L squared and LZ can have same with different eigenvalues, right? So by this we already know that they have simultaneous eigenvalues, but for mathematical purpose of checking, we can also show that if the two operators that we are talking about concerned here, if they commute with each other, then we must say that they will have simultaneous eigenstates. If if they commute with each other, then their this commutator bracket thing will be 0. Then so you can also show that if it acts on, let's say, YLM theta phi only, this operator commutator bracket, you are operating on this state, then you have L square LZ. So you again act this. So image cut is constant, it comes outside the operator range, and then L square again acts on YLM, so L into L plus 1 h cut square YLM theta phi. Minus when Lz operates on this thing, so this constant term L into L plus 1 h cut square comes to the left, and Lz acting on this will give you m h cut YLM theta phi, which is basically the same thing. So this is actually 0. So hence you can say that L square and Lz answer will be simultaneous eigenstates will be obtained by the two operators L square and Lz. So we can choose our answer. Lz and L square is only present for option number D. So option number D is the correct option. Now question number 2. For a spinless particle moving in potential VR, the time reversal operator T commutes with the Hamiltonian. That is true or false? Okay, so you have to show from a commutation relation whether the commutator bracket is 0 or not, and the operators involved will be time reversal operator T and the Hamiltonian, given that the potential of this system is already given in the question as VR. Now let us choose here. So the Hamiltonian of the system one second. Yes. Okay. The Hamiltonian of the system is potential energy plus kinetic energy. So kinetic energy plus potential energy. Kinetic energy, you know that P squared by twice m for the electron, and potential energy is always given in the question as the potential as PR, already given in the question. Now because it's a in the question you have to consider a spinless electron. So for spinless electron, what does time reversal operator actually do? So time reversal means going back in time, so t to minus t. Now if you operate this time reversal operator for your position, then your r vector under time reversal operator will be will be going to my r vector remains the same, plus r vector only. So on position does not it does not alter position like that, but on momentum it changes the sign of momentum, because earlier you were giving in one direction, now in the time reverse direction. So from P it will be going to minus P. So it alters the momentum. Why? Because you can imagine that earlier you were going in this direction, right? But now you are going reverse in time, so you'll be going in this direction. So if this is your T, this is for your minus T. So if your momentum here is plus P vector, then your momentum here will be minus P vector. So that is why your momentum direction will be altered by a time reversal symmetry or going back in time, but your position remains unchanged. So that is there, and then if if spin was actively considered mode in this case, then up spin under this time reversal operator goes to down spin. So if spin is there, then this happens, but here not applicable for our case, because already saying that it's to consider a spinless or without any spin consideration as given in the question. So not. No. So you have to find out what is this commutator bracket relation, right? Then if you now put down the formula or equation for each, so in terms of p squared by twice m plus v r that we just now have written, so you can divide the commutator bracket in two parts. So 1 by 2m constant can come outside, and t and p square will give you t. So you can decompose like that, and t here is the same. Now for calculating these individually, you have to know what is the values of these and this. So first of all, this t and vr is easy, that this will be equal to 0, because t with r is already, this is a position operator, with commutator bracket with t is 0, because this means that tr minus rt equal to 0, or tr equal to rt. Just 1 second. Okay, so you're saying that how the commutator bracket will behave in this case. So first of First of all, we have decomposed the whole commutation relation into two parts. One is having this t time reversal operator with the momentum operator p, and the other part has time reversal operator with the potential as a function of position, which is v as a function of r, right? So these are the two parts that you have to now figure out separately, that how the whole commutation relation will be uh, giving you. So first of all, what is T VR? This commutation bracket, I am saying that this will be 0. Why? Because you already saw that under time reversal operation, this position operator does not change anyhow. So the position remains unchanged. That means the commutation of T and R will be equal to 0. How we can say that? Because you can always write it like that. T and R commutation acting on a state psi, which is defining as a function r, position r. Okay, so then that is equal to commutation means this is t r minus rt acting on psi r. So r acting on psi r gives you only r psi r, the position r, minus r t acting on psi r does not change the position, so psi becomes psi. Now t can only act on psi r and not r, so this is t minus r psi r. Now t has literally no operational change on psi r if because it cannot change the position, so this is simply psi r psi r minus, so r cap acting on psi r also gives you r psi r, so this is equal to 0. That means you can say that if the time reversal operator is not changing the position of the state or wave function anyhow, then its commutation bracket relation with position will be giving you 0. That will be satisfied. So if that is 0, then you know that there is a this thing in the commutation bracket relations, that if you have a combination bracket relation 0 with position, then any function of position, which is in this case a potential, so that is also function of r. So then the potential operator will also be a basically a equivalent form of or similar form of the position operator r cap. So if t r cap commutation bracket is 0, then this will also be satisfied. So this is how we are taking this part to be 0. Now you can see there are two other terms coming into the picture, which is t and one other term, so t and p commutation bracket relation. So that you have to follow that how to derive that. So that how to do that. So t and p, this commutation bracket relation. So you already know that p, a momentum vector, goes to minus p vector if it is under the time reversal operator t cap. So if you go back in time, your momentum direction changes. That is very natural. So that means TP commutation bracket, which is basically TP minus PT. So instead of this, we have to write down that if under time reversal operation P is going to minus P, then uh, TP on psi a state psi. Now momentum operator, so it gives you the momentum. Now time reversal changes the momentum to minus p, but then again, what is p t psi? If you just change the order of the operators from p t p to pt, then t does not change anyhow the wave function psi. So that's it is only changing. Uh, Now this is p psi. So clearly see there is a sign difference. That means your uh, Tp is equal to minus Pt. So this is Tp, this is equal to minus Pt, because there is an extra minus sign that is coming here, which is not here. So once this is satisfied, you can say that your T and P anti-commutator bracket relation, so this is second bracket, that means anti-commutator bracket relation is 0, or your Tp plus Pt is equal to 0, your Tp is equal to minus Pt. So that is satisfied. So then you see that all of the terms you need here are already obtained. So here what you do is that T and H again let me write down. So now T and H is simply, because we are with commutation bracket with T already has given you 0, so you're only left with the kinetic energy term, which is P squared by twice M, right? So the term 1 says that if you take TH, then you are having T P squared by twice M plus VR. This is also the potential energy term. So then T P another P by twice M. Now we have seen from here that Tp is equal to minus Pt. So this is minus Pt plus VRT is basically TVR that we have already obtained, because this combination bracket of T and VR is already said to be 0. So if that is the case, then TV is equal to VT, right? So that is, I have interchanged the order. Now you can again take this as TP. Now TP is equal to again minus PT, so this is minus P this is plus P squared by twice M T cap. So you are getting P squared by twice M plus VR T cap. So you are seeing that you started with TH and you are obtaining back HT. Hence, the commutation bracket relation TH equal to 0 is satisfied. That means um, the Hamiltonian remains unchanged under T. So the statement of this problem was whether Hamiltonian remains unchanged under this time reversal operation. That is true, because whenever you satisfy a commutator bracket relation, that means in whatever order you take those two operators, the result does not change. So that means that whether you take your Hamiltonian first and then operate your time reversal operator, or you first time revert operate the state and then operate by the Hamiltonian, you will be obtaining the same result. So that means the Hamiltonians, when acting on the state psi, and then again time reversal is acting on it, so the Hamiltonian remains unchanged under the time reversal operation. So all of this can be concluded by only this proof that okay, T and H commutation bracket relation is 0. So that is one thing. So this commutes with the Hamiltonian, that is true. Now question number 3 is that consider an operator PR associated with the radial component of momentum small pr, and the operator r cap associated with the radial coordinate small r. Then their action on a radial wave function psi r is given by so the form of psi pr and psi r on psi r has been mentioned here. You have to find out what is the commutator bracket relation of the momentum operator pr and the position operator r. So by using those information, let us take it. Okay. So I have to find out what is this. Okay, and this is acting on a radial wave function psi r. That is already mentioned in the question. So then this is equal to simply PR Now PR. So if you look at the form of P operator given in the question, so this is minus I h cut 1 by R del R of R times whatever state it is acting on. So in this case it is acting on R psi R minus R cap operator acting on minus I h cut 1 by R. You take h cut I h cut as common, then this is plus sign, so this is R acting on del out of R psi R is basically psi R and then comes this term. So this is when the position operator operates on uh, psi R, you will be getting the position times the state back, right? This is I h cut R cap Okay, so I think we are missing out something on here. So let me check 1 by R del out of R psi R, right? So, okay. Uh, so when it's R psi R, so basically it is acting on the whole thing. So let me start again because I am getting confused whether I have made a mistake here or not. So let me start and rewrite again. That this is equal to minus I h cut 1 by R del R of R into R psi R, where this R psi R is coming from this operation. Then you have plus I h cut because minus minus making it plus, and then R acting over the whole thing. So naturally a position eigenvalue comes out which is smaller, and then the inner side state remains as it is, that is 1 by R del R of R psi R. Okay, so then this is equal to minus I h cut 1 by r square psi r makes it 2r psi r plus r square psi prime r plus I h cut. Then this r and this r can easily get cancelled out, only this part is under derivative, so this becomes psi r plus r psi prime r. So this is minus I h cut. This r and this r cancels out, so 2 psi r plus r psi prime r plus I h cut psi r plus r psi prime r. So you can see that this minus I h cut r psi prime r and plus I h cut r psi prime r, they cancelled out with each other, and you are only left with minus 2I h cut psi r plus I h cut psi r, which is minus I h cut psi r. So whenever you start from here and end up at this, so you can see that their eigen value relation has come as minus I h cut. So the answer is minus I h cut. So the answer will be option number A, minus I h cut. Okay. Now question number 4. Ground state wave function of hydrogen-like atom is given by this. Then if the interaction repulsion in helium is ignored, then the ground state wave function psi would be of what form? So hydrogen-like atom means, you know that hydrogen has only a single electron. So the single electron atom's wave function in ground state has a given form, and you have to find out what is the ground state wave function psi for a helium atom. Okay, and helium, you know that it is helium 2, that means it has Z equal to 2, or it has 2 electrons. So for 2 electrons, given the condition that the inter-electronic repulsion is ignored, then what will be the ground state wave function for the helium-like atom? So first of all, let me write down that hydrogen-like atom, that is single electron wave function at ground state is psi 100 is equal to 1 by root over pi now for helium atom. If as per the question their inter-electronic repulsion is ignored, then they act like single independent electron each. Now in the question it was mentioned at the end that if there are 2 electrons in this helium atom, then the position of the 2 electrons are R1 and R2 respectively. So then for each of these independently behaving electron, you will be having a ground state which is similar to this, because this is a single electron ground state, right? So for each of these electron, if you identify psi 100 as at a position R1 for electron 1 out of these 2 electrons in the helium atom, there will be having this kind of a form, only instead of R you will be replacing it with R1. And similarly you will be having psi 2 100 R2, which is the electron number 2 at a position R2, and also similar ground state wave function for this electron, only instead of R will be putting R2. So then the net ground state wave function of two independent electrons is psi, because they are not interacting with each other anyhow, so they are like independent of each other. That means you can calculate the net wave function as a product of these two independent wave functions. That means you have to take psi 1 100 r1 into psi 2 100 r2, which is, if you see that this common factor 1 by root over pi z by a naught 3 by 2, this thing will be squared, so 1 by root over pi will be 1 by pi, and then z by a naught to the power 3 by 2, when it is squared it is 3. Only you had exponential of minus zr by a naught. So now you have e to the power of minus z r1 by a naught and e to the power of minus z r2 by a naught. So you are getting 1 by pi z by a naught cube e to the power minus z by a naught r1 plus r2. So this is your answer, the wave function for the helium-like atom in the ground state for okay. So this is the answer we have obtained. Now we go to question number 5. So alright, so let us discuss question number 5 after this. So question number 5 says that consider a coherent state that is an eigenstate of annihilation operator such that the annihilation operator A operating on the state alpha kate is giving you alpha as eigenvalue and alpha kate back, right? So this is the eigenvalue equation for the annihilation operator A cap. Now the probability P of n of finding the state alpha in the number state n equal to 2 is this thing. Then you have to find out what is the value of q. So you can see two things. One is that you have to deal with the annihilation operator, and the second thing is that you have to know about the number state basis representation of that state, because whenever you know that you can represent a state out as a linear combination of the basis states, right? And then the probability of finding the main state in one of those basis states, you can just take the like what do I say, like the inner product of that basis state with the main state, right? So similarly in here we can try and attempt to write the main alpha kate, which is the state given here, that how can we represent any state uh, which is an eigenvector of this this annihilation operator. How can we represent that particular state in number of, in terms of the number state or n gates? So by that then we can solve the inner product and then get to know what is the value of q. So this is the idea, and I'll start solving it so then it will get clear. So question number 5 is, you have annihilation operator A cap acting on a state, let's say, for our advantage I am writing this state as psi ket instead of alpha ket, because I am writing only the eigenvalue as alpha. But you understand from the question that is psi ket is nothing but the alpha ket given in the question, right? Just for my convenience I am writing it down or renaming it basically as alpha ket. Now this is the eigenvalue equation for the annihilation operator A cap, right? Now if you have been familiar with the lecture notes, you know probably that you can represent the state psi ket as a linear combination of these states in the occupation number basis. So let's say n is the occupation number basis states. That means the value of n suggests that how many number of like what do I say, how many number of electrons or how many number of particles are there in a particular state. So like that, if n equal to 1 then you have only 1, if n equal to 2 then you have 2 particles, like that. So in each state how many particles occupy that state, that is given by this occupation number state n ket, right? So this can act like a basis state, means you can represent any arbitrary state psi ket as a linear representation, linear combination of these states in occupation number basis or basis states like this. So, and if you are familiar enough with this, you probably know that you can actually express this as if you know the eigenvalue equation, then the eigenket psi ket can be written down for this annihilation operator A cap particularly, that psi can be written down as e to the power of minus alpha whole mod square by 2 sum over n equal to from 0 to infinity alpha to the power of n divided by root over of n factorial and then n ket. So this is how you can represent the eigen function of the annihilation operator in terms of the occupation number state basis states. So this is the occupation number basis states, and this is the eigen ket of annihilation operator A cap. So how do you get to this? I am not going into the details how I am getting this, probably you already know that from the lecture, but to state very briefly, it comes from the relation that this annihilation operator when acts on this number occupancy state n, it actually gives you back root over of n minus 1 and n minus 1 ket back. So then if you act this on a state psi, which psi can be represented as Cn n ket, where n goes from 0 to infinity, and if A cap is acting on over that, then you can represent that this is equal to, so basically so A cap acts on this n, so what you get is that Cn n minus 1 root n minus 1 sum over n equal to from 0 to infinity, and you can redefine this thing as m equal to from 0 to infinity c of m plus 1 root over of m, and so we are redefining n minus 1 as m, then n equal to m plus 1. So sorry, I made a mistake. So here this is not root over of n minus 1 but root over of n. I confused it with the creation operator, but there will be only root over of n and not n minus 1. So this will be like this thing. So what are you getting is basically, so if it is an eigenvalue equation, then we will be getting alpha psi, where alpha is the eigenvalue, and alpha again psi can be written as m equal to 0 to infinity Cm m. So by comparing this and this, you can find out a recursion relation that says that Cm plus 1 is equal to Cm by root over of m plus 1 times alpha, right? So this is a recursion relation, you can say that Now if you like try this out repeatedly, then you see that C1 will be like alpha C0 by root over of 0 plus 1 equal to C0 alpha by 1 or root over of 1. Then C2 becomes your uh, alpha times here m replaced by 2 now. So sorry, m replaced by 1 now. So C1 divided by root over of 1 plus 1 equal to alpha times now 1 by root over 2. Then you replace C1 by what you got earlier, that is C0 times alpha, which is like alpha squared by root over of 2 C0, which is this. Now in similar manner you can find out that Cm actually is equal to alpha to the power of m divided by root over of. Now if you go on like this, you will see that this may be misleading if I just stop right at C2, but if you go to C3, now you will get that alpha times C2 by root over of 2 plus 1 is 3. That means you are getting alpha by root over 3 into C2 is alpha squared by root over of 2 C0. So you are getting alpha cube by root over of 3 factorial C0. So in a general form you can write Cm equal to alpha to the power m root over of m factorial C0. So this is your relation that you obtain from this recursion relation, and once you have obtained this part, you can see that you have gotten your Cm. So basically now you can now write down what is psi ket. So psi ket is equal to, then because it is Cn times Cn n ket, so n equal to from 0 to infinity. I am not writing it down every time, but it basically means n from 0 to infinity sum. Now this is alpha to the power of n root over of n factorial C0 n ket, right? So then this is equal to this is equal to C0 root over of n alpha to the power of sum over n alpha to the power n root over of n factorial n ket. Now if you normalize this state, so because eigenstate has to be normalized, that is mandatory, so then you get C0 whole mod squared sum over n, then you get alpha to the power 2n divided by n factorial, and you get n in this inner product equal to 1. Now these are already basis states, so this will be normalized already, so this is 1. Now C0 whole mod square is equal to simply you are getting C0 whole mod square sum over n alpha to the power 2n by n factorial equal to 1. Now this is a series expansion. You can see that this is, if you like go from n equal to from 0 to infinity, so alpha to the power 0 by 0 factorial is 1 plus alpha squared by 2 factorial plus alpha to the power 4 by 4 factorial, like this. So this is equal to 1. So you can see that this is nothing but e to the power of alpha mod of alpha squared, right? This series, because you know that any series of e to the power x is basically 1 plus x squared by 2 factorial plus like that. So also here I wrote down wrongly, this is not 2 factorial, this is 1 factorial, because this is n equal to 1, then alpha to the power 2 alpha to the power 4 by 2 factorial, like that. So here replace, here your x is replaced by alpha squared, and we have put a mod so that the alpha is not a complex, but it's the like modulus of the alpha is taken. So C0 becomes, because you have taken C0 modulus, so this is equal to e to the power of minus alpha squared by 2, basically because you are taking a square root, right? So you have gotten this. Now once you have obtained all these things, so you now know that you can write down your psi ket as sum over of n. Now value of Cn is independent of n, so we can basically write it down afterwards, like outside of the summation, e to the power mod alpha squared by 2 with a minus sign was there, right? And then sum over of n alpha to the power n by root over n factorial n ket. So this is the eigenket of the annihilation operator a cap written down in terms of the occupation number basis state n ket. So you can now you have known that how I am getting to this equation, right? Now once you have known this, now it is easier for us to further follow up, because you have been asked in the question that probability of the state to be found at n equal to 2 is basically p at n equal to 2 is nothing but the inner product of n equal to 2 to this state psi. So what you are getting is basically uh, so n. So basically you can see that these are all like summation or taken over n equal to from 1 2 3 4 to infinity. Now you know that because these n are orthonormal, they are ortho also means that they are orthogonal to each other. That means they are orthogonal and normalized. So any m and n inner product is equal to delta mn. That means it is equal to 1. So this is your Kronecker delta function. This is equal to 1 if m equal to n, and this is equal to 0 if m is not equal to n. So if that is the case, then you get that this is equal to all these n's except n equal to 2 will be getting you 0, because then this will be satisfying the orthogonal condition. Only for n equal to 2 in here you will be having an inner product of 1 and the value will be non-zero. So this is n psi for n equal to 2 you have to take. So this is basically e to the power of minus mod alpha squared by 2. Now instead of a summation you put a single term of n, so there will be no summation over n, just n equal to 2. Now this is alpha to the power of 2 by root over of 2 factorial, and then n equal to 2 and 2 will be 1. So this is alpha squared by root over of 2 to the power of minus mod alpha squared by 2 into 1. Now if you compare this with your given expression in the question, like if you go back, that this was e to the power minus alpha whole mod square alpha to the power 2q by q. Now okay, so instead of while talking about probability, you have to also, this was magnitude of that, sorry, the absolute value of that. So probability is basically whole mod squared, right? So like a state to be found in a state n, you have to take n psi, this inner product whole mod square, because it's not probability amplitude but the probability. So there will be a mod squared sign which we did not put earlier. So this thing, so this is anyway 1, so this whole thing whole mod squared. Now you get that this is alpha to the power 4 by 2 e to the power of minus alpha whole mod square. So now you get back to this problem, that you got e to the power of alpha whole mod squared alpha to the power of 4 divided by 2, right? So here alpha's power was 2q, so 2q equal to 4 and divided by was q, so q equal to 2. That means you are getting the value that q is equal to 2. So that is your final answer that it will be obtaining from here. So right, so you have obtained q equal to 2 as an answer. Now, question number 6. Using the properties of Pauli matrices, the expression e to the power of minus I pi sigma y by 2, sigma z to the power plus I pi sigma y by 2 turns out to be how much? So, here sigma are the Pauli matrices. Now, we have to simplify this expression so that you do not need to take the whole matrix multiplication to get to the answer, but you can simplify your answer by using the properties of Pauli matrices, right? Or the another thing is that you can also term by term take the matrix and then try to solve it, but that will be more like rigorous to do. Instead of that, you have been asked to use the property of Pauli matrices to simplify your problem. So here your question is that e to the power of minus I pi sigma y by 2 and then sigma z e to the power of plus I pi sigma y by 2. So this product you have to find out how, what is that. So now first of all you have an exponential with this with a theta angle, and then you have a what is that? That Pauli matrix multiplied to that. Now you can define that your Pauli matrix can have all three dimensions, like directions, like x cap, y cap, or z cap, but you can take your theta to be in that unit vector direction, like say in cap, and dot sigma. In cap is the unidirectional unit vector direction of this theta angle, and sigma vector is the matrix, Pauli matrix in this case. And whether you have sigma x or sigma y or sigma z, depending on that, this dot product will give you this kind of a value, where whether you have sigma y here, so then this y cap will be must be y cap, n cap will be n cap must be y cap, so that you get sigma y only. So like that you can define a dot product, and this theta is the angle, which in this case is pi by 2, you can see. So this is basically e to the power of I theta sigma vector dot n cap. Now this sigma vector dot n cap in our case is sigma y, so n cap is must be y cap, and here also theta is equal to pi by 2, but that we get to that later. So here theta equal to pi by 2, here theta equal to minus pi by 2. uh, just one second. So here we'll be using the property of the Pauli matrices, and as I said that this is how we can represent it like this, dot product of sigma dot n. Now to utilize the property of Pauli matrix, you know that Pauli matrix has this form that sigma I sigma j is equal to delta ij times the identity matrix I plus I epsilon ijk, which is you know that if they are in a cyclic order, then this is plus 1, and if not, then it will be minus 1. So like that, and if any of these two or three indices in two, or any sum of them are equal, then it will be giving you 0. So if that is the case, then from here your I, J, K can be your x, y, z basically. So this is the property of Pauli matrix. Now you have this sigma dot n, right? Sigma dot n you have. Now you want to take sigma dot n whole square. So sigma dot n whole square, if you take, that is equal to sum over uh, ni sigma I sum over I, and then because there is a whole square, so you have nj sigma j. So the unit vector, it has been multiplied with taken a dot product with the sigma Pauli spin matrix, and then there is a square taken, so you have two of them, right? Now you can take both of them together, like ij, and then ni nj, and sigma I sigma j. So here you can have ij nj, and then sigma I sigma j, you know from here you can replace that this is equal to delta ij I plus I epsilon ijk sigma k, right? Now if you take that delta ij under this sum, so you suppress one sum, you get ni equal to j, so ni squared, and then delta ij is 1, so into I, which is the identity matrix, plus I, which is this I is not the index I, this is the imaginary I, so we write it down like this I, and then summation over epsilon ijk, this sigma k. So this will be giving you so this is something that if you have to look very carefully, that ij ni nj and epsilon ij k sigma k. Now this part is something that is symmetric in I, j. That means even if you change the order of I and j to j to I, they even after that ni nj is equal to nj ni, right? So because ni nj is same as nj ni, but this part, this is asymmetric in ij, as epsilon ijk is not same as epsilon jik, because if you change the cyclic order, its value changes from plus 1 to minus 1. So when you have a summation, like a product like that with a symmetric term and an asymmetric term in I and j, so their product becomes actually gives you 0, because on one hand you will be getting, like, you can take a simple example, right? You can take the values of I and j like that. Like you can take I equal to 1 and j equal to 2. So I am giving you the example. Like say I equal to 1, j equal to 2, 1. So you have n1, n2, epsilon 1, 2, and so k is 3. So sigma 3. But the other term can also be that j equal to 1 and I equal to 2. Then you have uh, n2 n1 epsilon 213 sigma 3, because this summation gives you these two terms. Now you have this thing is plus 1, so this is plus n1 n2 sigma 3, plus this thing is minus 1 because its order has changed, but n1 n2 can be n2 n1, so this is this, so this is giving you 0. That means this product term, when given the summation over this term, because one part is symmetric and the other part is asymmetric, so the whole thing becomes 0. So you are only left with sum over of I. Now ni square is there. Also catch this n cap are unit vectors, right? So if this is unit vector, then you know their magnitude will be 1. So sum over ni square. So each of the components and whole square will be also 1. So this is like totally this is identity matrix, because this is I times 1 plus 0. So this is the identity matrix I 1 0 0 1. Now once you have obtained this, now you can have, like here you can see that you had a exponential times this I theta sigma dot n type of a situation. So you can write it down like this now, like I theta modulus has been taken because its direction has been taken care of in the dot product of sigma dot n cap. Now this can be written down as e to the power of I something. So this is, you can series expand this term. So this is like 1 plus ix by ix whole squared by 2 factor, like that. So you can, in a series form, you can how you can write it down is I theta to the power of so you can break it down into even series and odd series. So even power series are odd in terms of 2m. So here there you have I theta to the power 2m by 2m factorial into identity matrix I, where m goes from 0 to infinity, plus the odd term series will be like m equal to from 0 to infinity, but instead of 2m you have 2m plus 1, because you are meaning to take the odd powers in the power series. So this is 2m plus 1 factorial and then sigma vector dot n cap. So how I am writing it like that, so this will be clear to you. Like this is the even series partial terms and this is the odd power series. Right, so you know that this is like e to the power of ix sort of a thing. So this is 1 plus ix whole squared by 2 factorial plus dot dot. So there are even powers like um, uh, ix to the power 0 by 0 factorial plus ix to the power whole squared by 2 factorial plus ix to the power whole 4 by 4 factorial. So these are even power partial term, plus odd power partial term is ix plus ix whole cube by 3 factorial plus dot dot dot. So you can express it like this. Now the interesting thing is that here you have sigma dot n left, because in this case your x is nothing but I theta mod then sigma dot n. But you know that sigma dot n cap, just you have just derived the sigma dot n cap whole square is basically your identity matrix. So then what is your sigma dot n cap whole cube? So this is basically square times the main term. So this is identity matrix is the squared. So this is left with only sigma dot n. Similarly, if you continue, you will see that all even powers will be further higher powers of this term. So this will be giving me back the identity matrix. That means sigma dot n cap to the power of 2m, any even power will be giving you an identity matrix, and all odd powers, right? So where 2m plus 1 is there, so sigma dot n cap to the power of 2m plus 1 will be nothing but your simply sigma dot n, because whatever you multiply with this, the square term will be giving you the identity matrix, and the only term will be left with this. So odd powers will be having this term and even powers will be having this term. So that is why you have, apart from this powers, these factorial and these square terms, you have this identity matrix here, because the odd even powers are giving you identity matrix, and for the odd powers you are getting this, so that is why you have this term. So now when you have already simplified it like that, so you can now identify or recognize this series as nothing but your cos theta series. How? Because mm, cos theta series, because you are seeing that the first term is basically to the power m equal to 0, so this is 1, right? And then your next series will be like, okay, I theta to the power of 2m. Now, so the next part will be I squared theta squared. So this is I squared is minus 1. So this is theta squared by 2 factorial. Then for m equal to 3, this is for m equal to 1. Then for m equal to 2, you have 2 into 2 is to the power of 4. That is basically I to the power 4 means I squared squared. I squared is minus 1. That squared is plus 1. So this is to the power theta to the power 4 by 4 factorial. That is like, so you can identify immediately that this is nothing but your series expansion of cos theta. And what is the second term when you simplify it? So this is basically you are getting for m equal to 0, you have I theta to the power of 1, and then this is 2 plus 1, so this is 2 into 0 plus 1, that means 1 factorial. Then you have so you can take this thing as common and take the rest of the terms. So for m equal to 1, you have I theta to the power 2 plus 1, so I theta whole cube, 2 into 1 plus 1 is 3 factorial, plus all these terms, and then so sigma dot n cap is a common. So you know that I cube is I square into I, which is minus I, because I square is minus 1, and like that. So you can take your I as common. So only for this part you take I common. So you have theta, then I cube is minus I. So this is I, if you take I common, so this is theta minus theta cube by 3 factorial. Then the next term will be theta to the power 5 by 5 factorial, like that, and then multiplied with this term in the bracket sigma dot n. So this is also a familiar expression. This is the series expansion for sine theta. So all in all, you are getting the first term series expansion sum as cos theta plus imaginary I times series expansion giving you sine theta multiplied by sigma dot n. Now you have simplified your whole form of e to the power of I theta mod theta sigma dot n, which is also simplified as e to the power of I theta sigma. So this is your simplified form using the properties of Pauli spin matrices. Now once you have obtained this, so now things become easier, that you have, so you have this thing. So now what you had is that e to the power of minus I pi sigma y by 2, then sigma z e to the power of plus I pi sigma y by 2. So here your theta is your pi by 2 once, and once it is minus pi by 2. So for the first case it is minus pi by 2. Use this expression here. So this is cos of minus pi by 2 plus I sine of minus pi by 2, and sigma dot n is basically sigma y, because here n cap is equal to y cap, so this dot product is giving you sigma y, then sigma z, and next your theta is plus pi by 2, so cos pi by 2 plus imaginary I sine of plus pi by 2 sigma y. Now because you know that cos of minus theta is cos theta, so cos pi by 2 is cos of minus pi by 2, which is nothing but 0. So 0 plus, then I sine minus pi by sine minus pi by 2, so this minus comes outside for sine. So this is minus sine pi by 2, and sine pi by 2 is 1. So this is minus I into 1 into sigma y into sigma z, then cos pi by 2 is 0 plus imaginary I sine pi by 2 is 1, and then sigma y. So you have now that minus I squared sigma y sigma z sigma y. I minus I squared is plus 1. So this is sigma y, sigma z, sigma y. Now you already know that sigma y, sigma z is equal to from the Pauli's mean matrices formula, that this is this is I not equal to j, so the first term will be, so we will be using this formula, uh, this thing. So from here you see that sigma y sigma z is equal to delta I not equal to j, so this is 0 plus ij is x yz, so in the cyclic order, so xyz, then y z x z x y, cyclic order, it is plus 1 I into plus 1 into sigma x, so this is I times sigma x. So sigma y sigma z is equal to I times sigma x, and then again you are getting I sigma x sigma y. So again the first term Kronecker delta is 0 plus I epsilon ijk for xy in cyclic order is always again 1. So I times sigma z. So you are getting I squared sigma z, I squared is minus 1 into sigma z, so you are getting minus sigma z as your answer. So now let us compare whether it is the correct answer. So we are getting this turns out to be minus sigma z, so proportional to, okay, so it is basically proportional to sigma z will be the correct answer, because you are getting the answer as minus sigma z. Okay, so this is done. Now question number 7, the value of the expression lm lx squared lm, this is the expectation value taken of the operator lx square in the standard angular momentum basis will be out of this, which is the correct answer. So for that, so let us choose a blank page again and start solving. So you see the operator we have is lx squared, and you have to take an expectation value of that. So lx squared is there, and you have to take your expectation value lm like this. Now Lx square, you know that there is a direct eigenvalue equation known for L squared and Lz on the state Lm, but the direct eigenvalue equation is not there for Lx. So how to get to that so that you satisfy or simplify your problem? So basically to that, you take first with L squared equal to Lx squared plus Ly squared plus Lz squared. So your Lx squared becomes L squared minus Ly squared plus Lz squared. So from here you get to see that this is L squared minus um, um, L squared minus Ly squared minus Lz squared. Now plus, so you can write it like half. So you can write half L squared minus Lz squared minus Lx squared minus Ly squared plus Lx squared equal to Lx squared. Why? Because you see that this plus half Lx squared, when it comes to this side, you will be getting Lx squared minus half Lx squared, which is half Lx squared is equal to half L squared minus Lz squared minus Ly squared. So this half and half cancels out. You are again getting back to this part. So equivalently you can write it down like this. Okay, so this is the form. So why I am writing it like that? So basically you have, now you have, this is equal to half L squared minus Lz squared plus Lx squared minus Ly squared. Now the advantage of writing in this form is will be clear to you, that we can write now the expectation value Lm as half L squared minus Lz squared plus Lx squared minus Ly squared. So the importance of write it down in terms of Lx squared minus Ly squared is that, first of all, eigenvalue equation is known for L squared on Lm is basically L into L plus 1 h cut squared Lm. This is the eigenvalue equation for L squared operator, and for Lz operator it is simply m h cut Lm. So Lz squared will be m squared h cut squared Lm. But then you have because your for Lm there is nothing specific for x or y, so for x and y these will be, so the expectation value of x squared Lx squared will be same as the expectation value of Ly squared, since x and y directions are equivalent with respect to this state Lm, because they're independent of the choice of direction for x and y, but for z that is different, so that is why we cannot write it down like that. So that is why Lm, when you take Lx squared expectation like this will be the same as Lm Ly squared Lm, right? So that is why you can have this half outside, and you are basically taking the expectation value, so L square expectation value minus Lz square expectation value minus so plus Lx squared expectation value minus Ly squared expectation value. So this and this will be giving you 0 because these two are equal. So what you are left with is thus just this and this. So this is half L into L plus 1 minus m squared h cut squared. So what you are getting is yeah, so Lx squared you are getting as half L into L plus 1 minus m squared h cut squared. This is your answer. So this is only possible because you have very easily simplified this in terms of a form where you have a subtraction of Lx squared and Ly squared, so that because these are independent of the eigen function that is taken, so that is why whether you take the expectation value of Lx squared or Ly squared, they will have the same value. That is why their subtraction is giving you 0, and hence you are obtaining this term. So that is why when you go back to the options given to you, you'll be having h squared by 2. So this answer is your correct answer. Now question number 8, Heisenberg consider a particle in Coulomb's potential in 3D space. In Heisenberg picture, if the ddt of Lz expectation is equal to 0, where Lz is a z component of the angular momentum operator, then this would imply that H and Lz form share same eigenbasis. So the meaning of two operators sharing the same eigenbasis always means to say that they will be commuting with each other. That means H cap, so this is the basic rule in quantum mechanics operators, that H Lz, if their commutator bracket is 0, then your H Lz minus Lz H equal to 0. That means whether you change the order of Lz and H, the result will be remaining the same. So L cap H cap Lz operating on a state psi will be the same as Lz H operating on the same state psi. So this does not matter whether you take the order differently. So here Lz is operating on psi and here H cap is operating on psi. That means both of them can have psi as their eigenfunctions, because only after that H cap can again act on psi and Lz can again act on psi, and then LHS equal to RHS is possible. So here psi can be simultaneous eigenbasis of both the operators H cap and Lz cap if this condition is quantum mechanically satisfied. Also this Heisenberg's picture, this form you have to use. So let us use that and try to solve it. So question number 8 says that your Heisenberg equation of motion ddt of Lz cap is equal to 0 is given. Now you know that the operators has a time evolution which is represented by Heisenberg's equation of motion, where you can take the time derivative of an operator, and in this case the expectation value of the operator is taken, so all of them will have an expectation value is equal to del t of L z cap plus 1 by I h cut. So because there is an expectation value on the left hand side, all of the terms will have an expectation value like that, and this Lz is the other operator and each is the Hamiltonian operator. So in this case, because there is no explicit time dependence of Lz on t, so this part will be giving you 0 because it is the explicit time derivative, and the left hand side is already given to be 0 as per the question. That means you are having Lz cap h cap commutator bracket expectation value is equal to 0. That means you are having Lz and h cap commutator bracket equal to 0. Hence, because this is satisfied, so they can have eigenbasis as simultaneous. So this answers the question that simultaneous eigenbasis is true and possible for these operators under this condition. So our answer will be that they share the same eigenbasis, true, which is also the correct answer. Now question number 9 is that consider an electron subjected to a uniform magnetic field B is equal to B vector B is at z cap, where the vector potential A and the Hamiltonian of the electron is this thing. So where pi I is equal to pi minus EAI by C. The commutator bracket is you have to calculate. So here you can see the kinetic momentum is given as pi and the canonical momentum is given as p, so that you are already familiar that physically measurable momentum that gets changed by the vector potential is the actually the kinetic momentum, which in this case is pi. So pi x is basically px minus e ax by c, and pi y is equal to py minus e ay by c. So then your b vector is equal to b ez cap along z direction. So what is pi x and c by eb pi y squared. So we have to use the commutator bracket relations. So let us go down and solve this. This is pretty simple. Using the relations you will be getting the answer. So this is pi x and c by eb pi I squared. So you can write it down, you can break it up like pi x, pi y plus pi x, pi y, and this c by eb is a constant term, so it comes outside. So this is equal to this, and then pi x, pi y, commutator bracket is nothing but you represent pi x in px, my px minus uh, e ax by b, comma py minus a sorry this is by c actually, eay by c, and this is as per the relation given in the question is minus eax by c. So if you break it down, so we'll be having px py canonical momentum minus ea by c px ay minus e by sorry not e by a by c but e by c. So minus e by c pxay minus e by c axpy minus minus plus e squared by c squared axay. Now first of all px py will be giving you 0 because they are the same momentum, so because only x with px will be giving you ih card or y with py will be giving you ih card, all the other terms will be 0, so that is why. Similarly x and y, they are the same coordinates of the same function a, so their commutator bracket will also give you 0. So like that you have both of them 0. Now this thing you have obtained, that this is equal to minus E by C, right, minus E by C. Then you break it up, this commutator relation, Px Ay minus Ay Px, then this is Ax Py minus Py Ax, which is like so this is equal to minus E by C minus I h cut, Px equal to minus I h cut del x, and that del x will be operating on Ay, so del Ay del x minus Ay minus I h cut is minus minus plus, plus I h cut Ay del x. So remember that these are operators, so normal product will not work. You have to maintain the sequence or order in they are placed in. So now Ax Py is minus I h cut Ax del y, then minus of minus I h cut is plus I h cut, then this Py is at first, so this is operating on del x, so del x del Ax del y. So this is the final thing, right? So then you have this is equal to minus E by C minus I h cut del Ay del x plus I h cut Ay um, del x minus I h cut Ax del y plus I h cut del Ax del y. So this is the pi x pi y commutator bracket relation. Now in here you have C by EB common, and then you have 2 times this thing, but because they are operators, so one time the pi y is on the right and the other time is pi y is on the to the left, right? So then you have um, okay, so instead of this I think it would have been better to write it like this, that pi x pi y, if you represent it from here, instead of breaking it up further, if you take it up from here, if you take it up from here, then you have pi x pi y is equal to minus E by C minus, because here I have changed the sequence, so there is an additional minus sign here taking up. And you know that if you have any p x, if you take it with commutator bracket with some function f, then it will be giving you minus I h cut del f del x. Similarly, if you have any py and if you have any function p f prime, you will be getting minus I h cut del f prime del y. So just like that, you will be having uh, minus E by C minus I h cut del ay del x minus and minus plus I h cut del ax del y. Okay, so yeah. So these relations are known from let me okay. So once this is done, you have now to solve that this is equal to, you are getting this, and then you are having I each cut as common, so I each cut E by C. In fact, you can have minus I each cut as common, so this minus and minus makes it plus. Then you have this has become plus again, so this del Ay del x minus del x ax del y. So you know that curl of A is equal to B, right? So B is equal to nothing but x cap y cap z cap del del x del del y del del z, then ax ay az. So you can see only the z component of B is having z cap times del ay del x minus del ax del y. So you are having I e h cut by c bz. So thus you are getting this pi x pi y pi x pi y equal to I h cut by c bz. So here you are having c by eb. Now you replace what you have obtained pi x pi y I e h cut by c bz. So you replace it here, that this is I e h cut by c bz, then pi y plus pi y I e h cut by c bz. Now because this I e h cut by c bz, everything is a constant, so no operator form, so you can take it out as a constant term, c by eb into so this becomes 2 I e h cut by c, and then because bz is just a constant, so it comes to the left, and then only pi y. So you have e and because bz equal to b, there is no other magnetic field present except for the z component, so bz is only your b, so bz and b, this also cancels out, so you have 2, the c and c cancels out, so you have 2i pi y, 2i h cut pi y. So your answer becomes 2i h cut pi y. So let us go back and match our answer. So this is 2i h cut pi y. This is option number B. So we have correctly obtained that. Okay, so just using the commutator bracket relation and the basic formalisms of commutator bracket, you are obtaining this. Now the last question is the Hamiltonian of a spin 3 by 2 particle is so basically in last case we are getting this. Question number 10 is about spin third 3 by 2 particle. Hamiltonian is given where C and D are constants. Then the energy levels for such a particle with magnetic quantum number m equal to half is what? So Hamiltonian is given, right? C and D are constants. So what are the energy levels? Energy levels means you have to identify the energy eigenvalue, because H cap acting over some state ASM will be giving you some ESM. So you have to get this. Now there is C by H cut squared Sx squared plus Sy squared minus is z squared minus d by h cut is z. So the energy levels will be E Sm will be the expectation value of this energy Hamiltonian operator with respect to the state Sm. So here is equal to 3 by 2 just like J. So M can be minus 3 by 2 minus half plus half and plus 3 by 2 or all these four values. Now we have to identify first the energy eigenvalues and then put M equal to half only. So you take C by h cut square as a constant. So in the first term this is Sx squared expectation value plus Sy squared expectation value minus, so you can probably figure out what this term can be simplified into, that you know a squared has an eigen function relation with Sm state, but sy squared and sy squared do not have. So let us put the boundary here. So this is a squared equal to sx squared plus sy squared minus plus sz squared. So then sx squared plus sy squared is simply a squared minus sz squared. So you have c by h cut squared a squared minus sz squared, another sz squared. So a squared minus 2 sz squared, and the expectation value is taken, minus d by h cut, the expectation value is on sz cap. So from here, so you can take a boundary so that you can separate it. So this is c by h cut squared, a squared average minus 2 sz square average minus d by h cut is z average. So you have c by h cut squared s into s plus 1 minus 2 into ms squared, the whole thing is h cut squared. So this is basically the eigenvalue equation I have directly used. The eigenvalues minus d by h cut, sz has an eigenvalue of m h cut. So this h cut and h cut cancelling out. So this is c s into s plus 1 minus 2 ms squared minus m s d. So in this case ms has been asked to be taken as half. So you replace an s equal to already 3 by 2 given and m equal to half given. So you replace that here. So you have c 3 by 2 into 3 by 2 plus 1 minus 2 into half squared is 1/4 minus half is ms d. So this is c 3 by 2 into 3 by 2 plus 1 is 5 by 2. So this is 15 by 4 minus 2 by 4 minus d by 2. So this is 13c by 4 minus d by 2. So this is your answer. So let us separate this. This is your final answer. 13c by 2, 13c by 4 minus d by 2. So you are getting 13c by 4 minus d by 2, which is our option number B is the correct answer. So with this we have solved all the question in class assignment 9. So I hope it is clear.